All right, let's dive right in. Today we're going to tackle a classic problem from a book that I'm sure many of you know and love, or maybe know and fear, Irodov's Problems in General Physics. We're looking at problem 1.174. But look, this isn't just about plugging numbers into a formula. This problem is a really beautiful puzzle that shows you one of the most powerful ways of thinking in all of mechanics.
So let me just ask you this. When you see two objects moving around, what's the most natural way to describe what's happening? Well, probably from where you're standing, right? It just makes sense. But it turns out, in physics, sometimes the most powerful thing you can do is change your point of view. Let's see exactly why that is.
Okay, let's kick things off with what I like to call our tale of two viewpoints. And we're going to start with the most obvious perspective there is, our own. We're just standing still, watching the action unfold. Physicists have a name for this. They call it the laboratory reference frame.
So here's the scene. You've got two particles, one with mass m1 and another with mass m2. They're zipping along with velocities v1 and v2. And here's the interesting part. They're moving at right angles to each other. The problem also says the system is closed. That's just a fancy way of saying that nothing from the outside is messing with them. No pushes, no pulls.
And here's our mission. We need to find two things: the momentum of each particle and the total kinetic energy of the whole system. But here's the twist. We're not supposed to do this from our regular stationary point of view. We have to find these answers in some kind of special reference frame. And figuring out what that frame is and how to use it is the whole key to making a kind of tricky problem elegantly simple.
So what is this special viewpoint? Well, it's time to reveal our secret weapon for this problem. We're talking about something called the center of inertia frame. You might also hear it called the center of mass frame, or what we'll call it for short, the C frame. Okay, so what in the world is the center of inertia? Imagine for a second that you could take the total mass of both of our particles and just squish it all down into a single imaginary point. The C frame is the perspective that moves right along with that point. The easiest way to think about it, it's the system's perfect balance point as it flies through space. And we can actually calculate the velocity of this balance point, we'll call it Vc, using the formula you see here. It's basically just a weighted average. All that means is that the heavier particle has a little more say, a little more influence on where that center point is going. And you see those little arrows over the V's? Pay attention to those. That's to remind us that these are vectors. You have to add them like vectors, not just add their speeds. Super important. Now this right here is the superpower of the C-frame. If there's one thing you take away from this, it's this. If you were riding along on that imaginary balance point, looking out at the two particles, their total combined momentum would be precisely zero. Every single time. This is what makes it so useful for things like collisions, where everything seems chaotic from the outside. From the C-frame, it's all perfectly balanced. Okay, now for the fun part. Let's actually use this new tool of ours to solve part A of the problem. We're going to hop into the C-frame and see what the momentum of each particle looks like from in there.
You know, the process is actually a really simple three-step recipe. It's pretty foolproof. First, we find the velocity of the C-frame itself. Second, we figure out how fast the particles seem to be moving from the C-frame's moving perspective. And finally, we use those new velocities to calculate their momenta. So to find these new velocities, we'll call them V prime. All you do is take the original velocity and subtract the velocity of the C-frame. Now listen up, because this is probably the #1 most common mistake people make with these problems. This is vector subtraction. You can't just subtract the numbers. You have to subtract the entire velocity vector Vc from the original vectors V1 and V2, which means you have to account for their directions.
And what's so cool is what happens when you actually do the math for the new momenta. You find that P1 prime is exactly equal and opposite to P2 prime. They perfectly cancel each other out. This beautifully proves the point we made earlier. Their sum, the total momentum in the C-frame, is zero. It's not just a rule. You can see it right there in the math.
Okay, momentum is done. Let's move on to part B of the problem and see how this whole C-frame perspective simplifies the idea of energy. We're going to find the total kinetic energy of the system, but again, as seen from our special C-frame.
So, the formula for kinetic energy is the same one you've always known, 1/2 mv squared. But here's the key. We use the velocities as seen from the C-frame, those V prime values we just found. The number you get from this calculation has a special name. It's the internal energy of the system. You can think of it as the energy from the motion within the system, completely separate from the energy of the whole system moving through space.
And this slide just nails the whole point. The total energy that we measure from the lab is just this internal energy plus the kinetic energy of the system's center of mass moving along. The C-frame lets us slice these two apart cleanly. And what's really cool is that this internal energy, this T tilde, is the absolute minimum kinetic energy that any observer anywhere will ever measure for this system. That makes it a really fundamental property.
So we've solved the problem, check. But more importantly, we've uncovered a really deep idea in physics. So let's just zoom out for a second and think about the big takeaway here. So why did we go through all this trouble? Because the C-frame is like a physicist's secret weapon. It takes messy situations, like two things colliding, and makes them way simpler because you know the total momentum is always zero. It lets you separate the motion of a system from the motion within a system, which lets you see fundamental things like internal energy. And trust me, this isn't some one-off trick. It's a core idea you're going to see over and over again in physics.
And that kind of leaves us with one last thought. We started with a problem that seemed a little messy. You had perpendicular paths, vector math, and just by changing our point of view, we found a really clean, elegant solution. So maybe the next time you're staring at a tough problem, the first question to ask isn't, how do I solve this, but am I looking at this from the right angle? Thanks for joining me.